Hey everybody, this is Dr. White, and we are now on the topic of Bayesian estimation. So I want to take you back to an example we used when we first introduced Bayes' theorem, way back in the first chapter. What I want to do is recast that example so that instead of talking in terms of the probability of events, it talks in terms of distributions of random variables. And then we'll be ready to hit Bayesian estimation in the way that the book presents it in chapter 6. So back to that Roomie problem. Remember, you've got your room with you and your roommate sleeping in it, but eventually you wake up before your roommate does. And there's your closet here that contains 15 jeans, 5 khakis, and there's your roommate's closet, closet B, that contains just 3 jeans and 17 khakis. You randomly pick a closet because you are so groggy. You have a little bit bigger chance of picking your own closet, 60%, but a 40% chance of walking into your roommate's closet. So if you pick your own closet, your chance of picking jeans is 15 out of 20. But and your chance of picking khakis is 5 out of 20. But if you pick your roommate's closet, you only have a 3 in 20 chance of jeans. You have a 17 out of 20 chance of khakis. And what if you're walking to school after having picked out jeans, you open up your eyes, you're walking to school after having picked out your pants, you open your eyes, you look down, and you see that your pants are khakis. What's the chance they came from your roommate's closet? We needed the chance of B given K, and you remember what we did was we figured that using the definition of conditional probability, and then we used a version of the multiplication rule to write the top, and we used that conditioning technique to write out the probability of the khakis at the bottom. And the result is called Bayes' theorem. And it turned out there was a somewhat elevated probability, much more than 40%, that your jeans came from that your pants came from your roommate's closet. Well, anyway, let's rewrite this scenario using random variables and introducing some terminology that the book is going to use. Okay, so let's let capital theta, I'm trying to draw a capital Greek letter theta there. Let it be a random variable that is 0 if you choose closet A and 1 if you choose closet B. So it's a random variable that encapsulates the first part of this two-part process of getting some pants. The first part is picking the closet. The second part is picking pants from the chosen closet. How about that first part? Well, notice that capital theta is Bernoulli with a parameter P equal to 0.6, okay? Just the way, I'm sorry, that's 0.4. That is a typo. The parameter P is a 0.4 because it's a 1 if you get a closet B. And so this is also wrong. That should be probability 0 is 0.6 and probability 1 is 0.4. So I'm going to get something to write with and correct that in the version that you get to see on Canvas. Hold on a minute here. Okay, there we go. So Bernoulli 0.4. All righty. Now, once you look down, so it's like before you wake up and really open your eyes, you figure there's a 40% chance to have gone into your roommate's closet. That's sort of like your prior estimate on your chance of going into the roommate's closet. But now you've got some, data, and that data has a distribution that depends on which closet you pick from. Let's define capital Y given theta to be, it's going to be 0 if you pick jeans after having picked a particular closet, 1 if you pick khakis after having picked your closet. So actually there's 2 random variables here, 2 ordinary random variables here, each one depending on which closet you picked. So there's a capital Y given that the closet you've picked is closet A, Okay, so where the little theta is 0, okay, little theta is a possible value, capital theta. Um, and and so that random variable, I'm going to call that 0 if you pick jeans and 1 if you pick khakis. Okay. And then there's another random variable, the capital Y conditioned on theta is 1. That's where you pick the closet B. That again is going to be 0 if you pick jeans, 1 if you pick khakis. And so each of these random variables has a probability mass function, has a distribution. The distribution for the Y given theta is 0 is down here. So if you pick your own closet, then you've got a 15 and 20 chance for jeans, and you're supposed to write Y as 0 for that. You got a 5 and 20 chance for khakis, and you're supposed to write Y as 1 for that. And so that would be G of Y, given that theta is theta. The book uses little g for the PMF here. To write it more short, you would say G of Y given 0. Okay, and then this random variable has a PMF, G of Y given that theta is 1, G of Y given 1 for short, and its distribution looks like this. Okay. So actually, when you stick the two parts of the process together, you're looking at a bivariate random variable situation. Capital Y, capital theta. Okay? And so I can draw like a sample space for the bivariate situation here. I've got like a y-axis and a theta axis, and I've stuck the two possible values for y here. This is the jeans, and this is the khakis value. And the two possible values for theta here, this is the closet A value, and the 1 is the closet B value. And there's 4 points in the sample space. You know, there's 0, 0, and there's 1, 0, and there's 0, 1, and there's 1, 1. And there's a probability mass function for this bivariate distribution. And it's supposed to be written K of Y comma theta. That is a typo. That should be K of Y comma theta. So let me fix that. K of Y comma theta. Okay. And so like I could find each of those 4 values by basically, using some conditional probabilities, some conditional PMFs, and the multiplication rule. So like K of 0, 1. So that's the chance that Y is 0, that you pick jeans, and that the theta is 1, that you pick from closet B. So what's the chance that you pick jeans from closet B? Well, it's the chance that you pick jeans given that you went to closet B times the chance of closet B. So it's G of 0, 1 given the prior on closet B. And did I write down that the PMF for the prior is H? Yeah. The PMF on your prior shall be called little h. I want to make sure you keep that in mind. Okay, so in a similar way, you could find all of these values. This particular one came out to 3/20th times 0.4. That's this one here, but you could find all 4 if you wanted them. It turns out that when you actually do Bayes estimation work, you're not going to have to actually compute those values. But you just should know there's this bivariate situation in the background, capital Y theta. The data, the unknown closet. Okay, now Bayes' theorem, as done up here. Using this new random variable notation could be written like this. So here's that's your probability of, khakis and closet B, right? The joint PMF. And this is the probability of khakis, okay? the marginal for your capital Y random variable. The book calls the marginal for the capital Y random variable K1. I don't know why they do use these letters. It's just using that letters. Okay. And in Bayes' theorem, what you do is you use the conditioning technique to write that out in terms of G of Y theta and H of theta. And so here you are summing theta is 0, theta is 1. What's the chance of something given that you walked into your closet times the chance of walking into your closet plus, and then switch over to where theta is 1, chance of getting that thing given that you walked into your roomie's closet times chance of walking into your roomie's closet. And then on the top, you're using the multiplication rule to get that joint, just like we were doing up here. So I was wrong to say that you don't have to compute any of these probabilities. You're probably going to be interested in computing one of those probabilities, and you're using, that multiplication rule to get it. So Bayes' theorem can be written using these new letters if you write things out with with random variables instead of particular categorical events. So in our example, where we wanted the probability of closet B, given that you had drawn out some khakis, you were looking for G of 1 given 1 times H of 1 over the sum theta equals 0 to 1 of the G of 1 theta H theta. And I'm going to go ahead and kind of generalize that a little bit. 0 and 1 are the possible values of theta. Together they make the sample space of capital theta. And so I'm writing S of capital theta there. The sum over the little thetas in the S of capital theta is actually the sum that you're taking at the bottom when you do the conditioning. If you wanted the probability of closet A given khakis, there would have been a 0 here, and that 0 would also be shown down here. Now, very sadly, the textbook denotes this posterior probability of the theta given the y. They denote it as K of theta given y, even though they've already used K to denote the joint probability mass function. That is sad, but that's what they do. So we're going to have to write K of theta given y is this Bayesian theorem result. Now, that's the situation where your data is discrete, 0 or 1 like this time. Then you're summing over PMFs to get a probability on the bottom. But if your data is continuous-like, if it's continuous random variable in nature, then instead of summing, you're going to be integrating over the sample space for capital theta. G of y theta, h theta, d theta. And I'm sorry, let me take that all back. In this case, your parameter, your unknown closet was this discrete random variable, 0, 1, closet A, closet B. And so you were doing a sum here over PMFs. This H of theta was a PMF, okay? But it could be that your unknown, in general situations, it could be the unknown parameter in the first part of your random process is not discrete in nature, but continuous, in which case you'll be integrating over the sample space for capital theta, this d theta, okay? So in the book, they go ahead and just use that on the bottom for the conditioning. So imagining that you have a continuous unknown parameter, little theta. Okay. So let's again kind of review and make sure we got the terminology squared away. First thing is Little theta is some unknown parameter, some unknown number that helps to control the random situation that you've just been through. And it's treated as if it were a trial of some random variable capital theta. So you don't know which closet you went into, but the closet you went into controlled the rest of your process of picking out pants. It mattered which closet, you know. And we think of the closet you went into as a trial of this random variable, like pick a closet, you know. Point two, the distribution of capital theta. So you could give it with a PMF if capital theta is discrete. You could give it with a PDF if capital theta were continuous. But that distribution is called your prior distribution of capital theta. It's your prior on theta. Before you've got any evidence at hand, it's your estimate of the chances for little theta to be various things, for capital theta to turn out to be various things. And so in these situations, you're never really going to know what capital theta turned out to be. So you're never going to know what the little theta was. You're just going to have like estimates about the chances for what it could be. And you have here estimates of its chances before you take any data or evidence into consideration. You're just using your knowledge about the first part of that process, your knowledge about the chances of walking into closets. Okay, thing three, your evidence, your data, your capital Y, is always going to be conditional on what the value of capital theta actually turned out to be, what the little theta really is. And it'll generally be some kind of sample statistic, like it'll be the number of successes in trials, or it'll be a sample average, from, some distribution. But it'll be affected in its distribution by what a little theta really is. So whatever particular value that capital Y turns out to be, that's your data. So like in our problem, the data was khakis. We had on khakis. It could have been that we had on jeans. That would be another possible value, for the capital Y. Last point, what the book calls K of theta given Y is the posterior distribution of theta given your data, little y. And so that would be your new estimate of the chances for theta to be various things. Again, you'll never know what theta was, but you'll have a revised estimate of the chances for it to be various things using Bayes' theorem. So let's try another application of Bayes' theorem. So for a different kind of theta and a different kind of evidence. Say you've got a population of basketball players, some big population of basketball players, and each of them has a free throw hit rate, a probability of making a free throw when they try. Each one has their own probability, but when you stick them all together, if you like make a big histogram of their probabilities, it turns out to look like a PDF for a beta curve, a beta distribution with parameters alpha and beta. And let's say you're told about that population. You know about that population. You know that beta curve. You know the alpha. You know the beta. Okay? And what's going to happen is that a player is picked at random from this population. Okay? You don't know that player's hit probability. Call it little theta. So as far as you're concerned, since she was picked at random from that population, her theta is a trial of this random variable capital theta, whose PDF is given by the PDF for a beta alpha beta curve. So the possible values for little theta are a probability of hitting between 0 and 1. And here's the height of the density curve at that particular little possible value. Okay. So you don't know where theta, but you wish you could estimate it. All right. So why don't you have her shoot in free throws? And let's let capital Y be the number of free throws that she makes. So the capital Y, given her hit probability little theta, that's going to be binomial with, in trials, each shot being a trial, chance of success theta on each try. And the PMF for that binomial would be written G of Y given theta, where Y is a possible number of hits. Now that could be anywhere from 0 to little n, number of hits. And the chance to have exactly n hits would be the n choose y, theta to the y, 1 minus theta to the n minus y, PMF that you know for binomials. Now you would like to find the posterior PDF for the theta, given that the capital Y turned out to be little y. You're looking for that k of theta given y. And Bayes' theorem says that it is this. So the theta this time is a continuous type random variable. So in the bottom, we got one of these integrals. Let's write in everything we know. G of y theta, that's the binomial PMF, the chance of making y shots out of n, given that she has a theta chance each time. What's the chance for capital theta to be little theta? This. What is the chance that she hits y shots? That's what's on the bottom. Here you are adding up the chance of y given theta times the chance of theta for all the possible thetas. You're doing the conditioning to get the chance of exactly y shots. And so it's this big nasty integral here that goes from 0 to 1 because that's the sample space for your capital theta this time. So it's pretty horrid integral down there. But I noticed there's like, there's a constant that could factor out and cancel with this thing on the top. And I'm sorry, no, that stays. Oops, does that stay? Oh, no, it doesn't. That should say d theta right there. That is a typo. That is a typo that I want to fix right away. That should be a d theta right there. Okay. And so this n choose y, that's a constant. It can factor out of the integral, and it's going to cancel this n choose y here. Sorry. There's this other constant that could factor outside the integral, and it's going to cancel this constant up here. So things don't look that horrible. I guess there's also some things you can combine. Theta to the y can combine with theta to the alpha minus 1, and these 1 minus theta doohickeys can combine as well. And I've done that combination here on the top. And I've got this kind of semi-nasty integral down on the bottom. And I guess the next natural move would be to evaluate that semi-nasty integral, which could be done. It could be done in a tricky way using your knowledge about the beta distributions, so that you don't have to do any real calculus there. But I'm going to be even more tricky and just notice that when you got done with that integral, there wouldn't be any thetas left. There would be maybe alphas and betas and y's, but the variable of integration is theta. That's going to be gone. So whatever you get on the bottom, it's a number that does not involve theta. I'm just going to write it as a C. And then the rest of the stuff here, I've just done a little different recombining. Y plus alpha minus 1, I've written as alpha plus y minus 1. And this n minus y plus beta minus 1, I wrote it as beta plus n minus y minus 1. And so that is your chance for theta given y for all your thetas. Okay. So this is your posterior PDF for the theta given y. It's a PDF. And you know what? That has that part that depends on the theta, that has the form for the PDF of a beta distribution. where the first parameter is alpha plus y and the second parameter is beta plus n minus y. Now, there can't be two PDFs that both have the same quantity depending on theta, but different constants in front. You can't have like the beta that does that and this other one that does that. The reason is they both got to integrate to 1 when you integrate over the sample space of thetas. When you integrate, theta goes from 0 to 1. They're both going to have to integrate to 1. And so you can't have this be any different than whatever constant stuff came in front in the PDF for a beta. Therefore, this stuff must be that stuff. This must have been the beta distribution all along. And it had this extra stuff in front because that's what goes in front. First parameter and second parameter put together. So the posterior distribution for the capital theta, given y hits and n tries, is again a beta distribution. And all you got to do to find it is add on the y hits to the alpha parameter that you already know for that population of basketball players. And the n minus y failures, add that on to the beta parameter that you already know for that population of basketball players. Wow. So, like, what do you think about this player now that you've seen her make y hits in n tries? What do you think her theta might be? Well, before you had data, a good guess at what her theta might be would be the average for this population, the mean of this population. And so that would be the mean of that prior beta random variable that gives the shape of the population. So that's the expected value of a beta alpha beta, which is alpha over alpha plus beta. But afterwards, your best guess would be based on the posterior. What's the mean of the posterior distribution for the theta? Well, it would be alpha plus y over alpha plus beta plus n, which is pretty simple. You just add on the hits to y and add on the total number of tries to the alpha plus beta. Hits on top, total tries on the bottom. And boom, you get this new fraction represents your new best single point estimate of her theta value. And there's something very interesting about that. That new estimate, the book calls it W of y, because it depends on y, right there. WY, if you do a little algebra, can be written as this weighted average of two things. The two things are y over n and alpha over alpha plus beta. Now, alpha over alpha plus beta, you could call that your prior only estimate. That's the best estimate you could make if you never looked at any data. Best estimate you could make of her theta. On the other hand, if you don't pay any attention to prior, if you don't give any weight at all to the prior, and you just look at what she did for you, then wouldn't you guess as her theta, wouldn't you guess the number of times she made it divided by the number of times she tried? That would be a data-only estimate of her theta. And this is a weighted average of those two. I mean, if you check it out, this number here and this number here add up to 1. And so you're giving a certain percentage of weight to the data-only estimate and 100% minus that percentage weight to the prior-only estimate. You're kind of splitting the difference between the two estimates. Your Bayesian estimate of the theta is somewhere in between those two estimates. It's paying attention to both the prior and the data. Notice also, as the number of shots you take goes up, and the more data you get from her, the closer that fraction is going to get to 1, And the closer this fraction is going to get to 0, because you're not changing the alpha and the beta. The n's changing here as n goes to infinity. And so what's happening is the very sensible thing that the more data you get from her, the more weight you're going to give to the data-driven estimate, and the less important that population that she came from is going to be in your mind when it comes to thinking about her. It gets even better. That posterior distribution that you found based on your data, that can become your new prior, and then you can get further data and then make further revisions. And it's really cool that that new prior is still a beta like the old prior was. When the posterior is like the prior, like that, when they both come from the same family of distributions, then we say that that pair, that bivariate random variable, the theta, the capital theta random variable, the capital Y random variable, we say that they're a conjugate pair. And there's several important conjugate pairs in the basic theory of Bayesian statistics. You've met your first one. This one is called the beta-binomial pair. Prior beta, data is binomial, resulted in posterior beta. So now your iteration in the face of further evidence is really kind of easy. So let's call the Y hits, let's say it was Y1, out of N1 shots. Say that was your initial data. Well, so taking the data into account, then your posterior would be beta alpha plus Y1, beta alpha plus Y1, beta plus N1, should be an N1 there, minus Y1. Because but now suppose that you give her some more shots to try. You say, take another N2 shots, and say she makes Y2 of those. Then your new posterior all you got to do is just add on the Y2 to what you had before. Add on the N2 minus the Y2 to what you had before. And so it's very, very easy in this situation to get that new posterior because you're working within that same family. You're just making these sort of data-based adjustments to the parameters that define the family. So not only is iteration easy, also, after you have data, you're more certain about where the unknown theta is than you were before. The expected value of theta prior was alpha over alpha plus beta. The variance in that estimate was the variance of the beta distribution, which is that. Now you got your new estimate, your new posterior estimate, alpha plus y over alpha plus beta plus n. And that has a variance. And the variance of that beta distribution, same idea. So first parameter, second parameter, sum of the parameters plus 1, sum of the parameters. Same as here, you're just putting in the new parameters. And if you look at that fraction, I guarantee you this fraction here is going to be smaller than this fraction. The reason is that it's composed of an alpha over alpha beta plus 1, and it's composed of a beta over an alpha plus beta. Now, if you look at the alpha plus y over the alpha plus beta plus n plus 1, you've added on a y to the top, but you've added on more to the bottom. You've added on n. And so this little fraction here has to be smaller than this fraction here. Similarly, this second fraction, this over this, it comes from adding less to the top than you did to the bottom. And so it's going to be smaller than this second fraction right here. So the new variance, the posterior variance, is less than the prior variance. So you're more sure that theta lies in a narrower range after you've got your data than you were before. One way of making that more precise is to give what we call a confidence interval, a range of reasonable values for theta using that posterior distribution. I call it a confidence interval. It probably should be called a probability interval in Bayesian thinking, because in Bayesian thinking, you really do have this probability distribution for theta given your data. And the way that the Bayesians construct such a reasonable range is they might say, I would like a 95% probability interval. So I will go to the 2.5th percentile of my posterior distribution. So here's like that posterior beta distribution, maybe graphed, going from the 0 to 1. I'll go to the 2.5th percentile, so that's called theta 0.25. And I'll go to the 97.5th percentile, theta 0.975. And the range between them would have 95% of the area under the posterior curve between that lower and upper bound. And so the probability that theta lies in that bound would be 95%. So that bound is called by Bayesians a 95% probability interval for theta. So intuitively, if she makes Y hits and N tries, there's a 95% chance that her theta lies inside this interval. This is pretty neat. Why don't we go to R and work out an actual example? So I've got an R script that you'll get up on the server eventually by the time you see this screencast. So we've got our basketball player, and let's say that she's a random pick from a population that we know is shaped like a beta 8,2. The alpha is 8, the beta is 2. So what would be your point estimate for what her theta is without any data to consider about her, just the fact that she comes in this population? So I would suggest using the mean of the population. So alpha over alpha plus beta, so that would be 8 over 8 plus 2, 8/10, 0.8. Your best guess is she has an 80% chance of making each shot. If you had to make a probability interval right now, like a 95% probability interval, then you would go for the 2.5th percentile with Q beta and the 97.5th percentile with Q beta, shape 1 and shape 2 given by 8 and 2 respectively. And so let's give that a try in the console. I get 51.7% for the lower bound. For the upper bound, I got 97.1%. 57% to 97%. Big range. Best guess is 0.8, but it could reasonably be anywhere between 52% roughly and 97%. But let's have her take 100 free throw shots and say she only makes 65 of them, 65%. A little bit below average for the population. What's your new best guess for her? Well, the posterior distribution for her, based on her data, is beta 8 plus 65, 2 plus 35, because she had 65 successes and 35 failures. So that's a beta 7337. So what's your new point estimate? Well, what's the expected value of a beta 7337? It would be the 73 over the 73 plus the 37. 73 over 110. Let's give that a try. That's 66%. So even though she only made 65% in these 100 tries, you're still thinking she might be a little better than that. And that's because she comes from a population where this average was 80%. Now, what's your new 95% probability interval? Well, the lower bound would be the Q beta 0.025 new parameters. I've got 57% now. Upper bound, 75%. 57% to 75% is a much narrower range than the original 52% to 97%. We're getting more sure of where her beta is because we have more data. If I were to give her like another 100 shots and say she makes 70 out of the next 100, then what would be my new interval? Let me just copy these upper and lower bounds, paste that in. Let me see, if she makes another 70 out of 100, then I've got to add a 70 to the 73 here, so it's a 143. She missed 30, so I got to add a 30 to the 37. So let me change those. And now my lower bound is up to 61.6, and my upper bound is at 74%. Narrower still. And what was my new estimate for her? So instead of 73 over 110, it is now a 143 over 210, just adding all the successes and the failures. And that is 68%. And so the more data you get from her, the narrower the 95% interval is going to get, the more it'll hone in on, what her real theta is. So that's all we've got for the first part of our treatment of Bayesian estimation. We probably need to look at a couple of more cases where there are famous conjugate pairs. It looks like there's going to be some nasty integration to deal with. Those integral on the bottom look bad, but don't worry. You will often not have to, do any work with those integrals, and that'll be nice. You'll be able to use a trick kind of similar to the one that I used just now. So we'll look at a couple more classic examples, and then do some computations with them as well in a future screencast. See you soon.